Okay, Manjil, can you start?
Yes.
Okay, so very good afternoon to all of you present, so all of the present who are here. So at first I welcome you all for this Friday seminar. So today for this seminar we have a speaker, Dr. Manjil Saikia. So let me briefly introduce about Manjil. Manjil has done his integrated MSc from Tezpur University, and he has also got Instar Fellowship at that time. And then he, from 2014 to 2015, he has done his postgraduate diploma at International Center for Theoretical Physics, Italy, in mathematics. Then he has done his PhD from University of Vienna, Austria, from 2015 to 2019. After that, he has now currently he is working as a postdoctoral research associate at Cardiff University, UK. So he is mostly working in number theory. So today he will going to speak on combinatorial reciprocity theorem and some examples. So please, Manjil, you can start.
Thank you so much. First of all, I would like to thank Dr. Raut and the Institute of Mathematics and Applications for the invitation. I am very pleased to be here today and to see so many of you in the talk. Let me share my screen. So I have not done this before. Can you tell me that if my screen is visible or not?
Yes, yes.
Okay, I can
Yes,
see
yes.
it. Yeah. So apologies because there is some problem with the laptop. I cannot connect the audio and video from the laptop. So I'm connecting the audio from the phone. I'll stop the camera. Otherwise, you'll just see the ceiling of my room because I have to put down the phone. Apologies for that. So can you still hear me?
Yes, 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 yes.
Okay. So today I'm going to speak about combinatorial reciprocity theorems. Actually, I'm going to give some basic examples of combinatorial reciprocity theorems. And whatever I'm going to speak can be found in a book of the same name by Matthias Beck and Raman Sanyal. So the name of the book is Combinatorial Reciprocity Theorems. The authors are Matthias Beck and Raman Sanyal. So this is a book published by the American Mathematical Society, and it's in their Graduate Studies in Mathematics series 195. So this was published, I think, 2 years back. It's a very nice book. It has 7 chapters, and today I'm going to speak about what is basically chapter 1. So just to give an idea, so this book is about geometric combinatorics. It deals with polytopes, posets, graphs, and so on. And I think with an undergraduate background, the students can appreciate the material in this book. So there is another very nice book by Matthias Beck and Sinai Robbins called Computing the Discrete Continuously, which is an undergraduate text published by Springer. That is also a very nice book and has some parallels with this book. But this is the main reference if someone wants to take a look after the talk. Another reference would be a paper by Richard Stanley. Basically, it was Stanley who started this whole business of combinatorial reciprocity theorems. This paper was published in 1974 in Advances in Mathematics. And the title of the paper is same, Combinatorial Reciprocity Theorem. So if somebody is interested in more examples, then they can look at this paper after the talk. Okay, so let me begin. As already mentioned in the abstract, a combinatorial reciprocity theorem relates 2 classes of combinatorial objects via their counting functions. So consider a class, say X, of combinatorial objects. Oh, I'm sorry, I forgot to mention that if there is some issue or some question in the middle of the talk, please feel free to ask me. So I'm not a proper expert in combinatorial reciprocity theorems. I just like combinatorial reciprocity theorems, and I think it's something which is worth discussing with students. So I selected this topic. Okay, so coming back, consider a class of combinatorial objects, and let Fn be. So let Fn be the function that counts these objects. That counts the number of objects in X. So by number of objects, I mean it might count some property of the objects X, or it might count the whole class of objects in X. So it's up to us how we define this counting function Fn. Okay. So for example, if X is the class of all n by n matrices, then it might count all the number of n by n matrices, or it might count all the matrices which have diagonal entries 0 or something like that. So it's up to us how we define this function Fn. Okay, so in X of size n. So we need two things to happen for a combinatorial reciprocity to occur. So we need the following two things to happen for a combinatorial reciprocity to occur. And okay, so the first thing that has to happen is that the function Fn is the restriction of some reasonable function, for example, a polynomial, to the positive integers. So in all our cases, actually, the examples that we're going to see today will, in all these cases, Fn will actually be a polynomial in n. So for our case, this reasonable function, we can take this to be a polynomial. The second thing that has to occur is the following, and this is the important bit. So the evaluation f minus n is an integer of the same sign. Say sigma equal to plus minus 1 for all n in the set of integers, positive integers actually. So what is important is that if you evaluate Fn in the negative integers, then that is also an integer, and those integers are all of the same sign. So either positive or negative, and we are going to normalize this sign. So if it is negative, we are going to normalize it, so by multiplying it with the appropriate factor. And if it is positive, then there is no normalization needed. So these are the two things which we want for a combinatorial reciprocity to occur. And as a combinatorialist, the most natural question that you can ask is, suppose you get some sort of function like this, f of minus n, where all of the corresponding output values are of the same sign and are integers, then the most natural question that you can ask is, does this function f minus n have a combinatorial meaning? Okay, so a very natural question for combinatorialists. Is the following. So does sigma of f of minus n have a combinatorial meaning? So what do we mean by combinatorial meaning? For combinatorialists, if you can associate some sort of set of objects whose counting function is given by this sigma of f minus n, then we'll say that this function has a combinatorial meaning. Okay. So let us look at a very basic example, which is, I mean, it's almost sort of a non-example, but this would be what a basic example would look like. So let us consider the class of maps from this set to the set of positive integers. So this is basically from the set k, which is equal to 1 to up to k into positive integers. So then let's say Fn counts the number of such maps. So I'm sure all of you are familiar with this counting function Fn. So Fn is basically given by n to the power k, because each of these values 1, 2 up to k has n choices. So I mean, into positive integers, say our codomain, if we take to be n, which is nothing but 1, 2 up to n, then we can associate each of these number 1 up to k with any of these n numbers, n integers. So Fn will be equal to n to the power k. Okay. So this basically Fn counts the number of such maps with codomain n. Now let's see if it satisfies the two conditions that we have. So the first condition was that Fn has to be a restriction of a polynomial, and this is already a polynomial in n. So the first condition is satisfied. So Fn is a restriction of a polynomial. Then the second condition was that sigma of f of minus n has to be has to have the same sign. So let's see what is f of minus n. So f of minus n here is minus n to the power k, and this is minus 1 to the power k times n to the power k. So if we normalize it by minus 1 to the power k, that means if we multiply this minus 1 to the power k here, then what we get is n to the power k back. So the evaluation f of minus n has the same sign with some normalizing factor, and this is equal to actually f of n itself in this case. Okay. So this also satisfies our required second condition. So the first condition and the second condition both are satisfied in this example. So what is the combinatorial reciprocity that we get? We get back the same thing actually here. So this is that is why I call this a non-example, but it's still an example. So the combinatorial reciprocity that we get is, so this relates the number of maps k to n into itself. Okay, so this is an example, a very basic example of a combinatorial reciprocity theorem. So let's go to a more interesting example. So let us go to the second example now, and this example is taken from John Riordan, who was a very famous combinatorial mathematician, and he has a very nice book on I think it's called Combinatorial Analysis, if I'm not mistaken. So it's a very nice book by John Riordan. Okay, so this is also an example with which you are all familiar with. So for a set capital S and D an integer. So for me, actually, if I call something an integer, it's almost always a positive integer, sometimes including 0. So the collection of D subsets of S is defined in this way. So S choose D. These are the collection of all sets A, which are subsets of S, such that the cardinality of A is equal to D. Okay, so these are the D subsets. So for example, if our set S is say 1, 2, 3, 4, and D is just 1, then S choose D, which is equal to 1, 2, 3, 4, choose 1. This is nothing but 1, 2, 3, and 4. So these are the sets. Okay. So for a fixed D, the number of D subsets of S, they depend only on the cardinality of S. Depend only on the cardinality of S. Okay, and the number of D subsets of an n set, so which is basically a set which has n element, is now given by our counting function fn, which will be equal to n choose d. Okay. So there are n elements, and we want to count all the number of subsets which have d elements each. So basically, we are going to choose d elements out of n elements. So the counting function fn is just n choose d. And this you can write it as a polynomial. So this is nothing but n minus 1 up to n minus d plus 1 divided by d factorial. So this is just the basic definition of a binomial coefficient. And already our first condition is satisfied, that this fn is now a restriction of a polynomial in n of degree d. The degree of this polynomial is d, because there are d many terms in the numerator. Okay, so the first condition that we have is that fn is the restriction of a polynomial in n of degree d. Let's look at the second condition. So what is f of minus n? So I'm going to normalize it later on. If there is a negative sign, I'm going to just normalize it with the appropriate power of minus 1. So let's look at f of minus n. So f of minus n is minus n, then minus n minus 1, minus n minus 2, up to minus n minus d plus 1 divided by d factorial. So if so there are d many terms in the numerator, so I can just take out minus 1 to the power d here. Then what I am left with is n plus 1, n plus 2, so on up to n plus d minus 1 divided by d factorial. And this is nothing but minus 1 to the power d, n plus d minus 1, choose d. Okay. So if you want to see it more carefully, let's look at this. What is n plus d minus 1 choose d? So this is n plus d minus 1 factorial divided by d factorial, then n minus 1 factorial, which is nothing but n plus d minus 1, n plus d minus 2, and so on. And then this will stop at n, because after n minus 1 factorial, it will get cancelled. So the term before this will be n plus 1 n divided by d factorial, which is the same thing as what we had here. Okay. So our fn is equal to minus 1 to the power d times n plus d minus 1 choose d. So I'm going to normalize our fn. If I multiply it by minus 1 to the power d, minus 1 to the power d fn, we'll get n plus d minus 1 choose d. All right. So now this is a very nice binomial coefficient. And I mean, whenever we get a binomial coefficient, we'd like to associate it with some sort of object, combinatorial object, which is counted by that binomial coefficient. So one easy example would be just that these are the d subsets of n plus d minus 1 set. But I'm not interested in that, so I want something else. And what is this? This is nothing but the number of d multisets, d multi-subsets of an n set. Okay, so if you don't know what is a multiset, so in a set, each of the elements, they occur only once, but in a multiset, each element can occur more than once. Okay, so for example, 1, 1, 2, 2, 3, 4, 4, 5. This is a multiset of the elements 1, 2, 3, 4. Okay, so what is this? This is this is the number of ways of picking d elements from the set 1, 2 up to n with repetition. Because this is a multiset, so our repetitions are allowed with repetition, but without regard to the order. So the order is not important. So this is a very nice example of a combinatorial reciprocity, where we started with the function fn, which was just the number of d subsets of an n set, this function, and then we calculated this function at the negative values and found that, okay, this is also counting something with proper normalization. So this is another example of a combinatorial reciprocity. We are going to see at least two more of such an example. But before going further, if there are any questions, then I can answer them. Okay, so let's go to a more
Excuse me, sir.
serious. Yeah.
Hello. Sir, actually, I'm not getting the. I mean, why do we study the? Why do we? What is the need to study the combinatorial reciprocity? Any some application? Some. It will be useful if you give some application, right? So,
Yeah. So this is a question which
I mean the.
I
I mean the very basic meaning that. What is the meaning of combinatorial reciprocity theorem? So can you please repeat again, sir? Please better.
Yeah, sure. So as I said, so combinatorial reciprocity, this is basically connecting two different class of objects which are counted sort of like by the same function fn. So if you calculate fn in the positive integers, then you get some particular object x, and if you calculate fn for the negative integers, then you get, with proper normalization, then you get some other objects. So this is basically sort of like a connection between two different class of combinatorial objects. As for examples, so there are obviously mathematical examples of combinatorial reciprocity helping things. For example, in the next example that I'm going to discuss, this is about graph colorings, and the whole concept of like the function that I'm going to study for graph colorings and combinatorial reciprocity, it started out of studying the four-color theorem, which is a very important graph theoretic result, which was finally proven after more than 100 years in 1980s, if I'm not wrong. So, and graph theory has a lot of connections with networks, with
Yes.
social networks, and with many other things in telecommunications, communication theory, and so on. So, so this has some sort of practical application, but for me, there is no. So for me, there is no end goal of an application in my mind. I just like this because it's an interesting mathematical thing, combinatorial reciprocity. So I mean, in this
Okay.
talk, I'm going to discuss any application.
Okay. Thank
All right, so let's go for a more serious example now. So which is related to graph colorings. So for graph colorings, I need the definition of a graph. So a graph is basically, so I'm not going to be very rigorous with this definition of a graph. So I'm assuming that most of you know what is a graph. So a graph G is a collection of two sets, basically V and E, where the set V are called nodes. The elements in the set V are called nodes, and the elements in the set E are called edges. Okay. So if V and U are some nodes, and if they're connected, V and U are connected, then we write VU to be an edge. Okay. So the thing that is important for a graph and what makes it more interesting is that you can visualize these graphs. So for example, if you have certain nodes, say 4 nodes, so 1, 2, 3, 4, and then if you just connect these nodes in whatever way you would like, okay, so this is a connection. So this gives us a graph. Okay, so here the set V is 1, 2, 3, 4, and the set E is 1, 2 because 1 and 2 are connected, 1, 3, 1, 4, 4, 2, 2, 3, and 2, 3. So since there are two connections between 2 and 3. So such a connection, if we have two connections between two particular nodes, then we call these as a this graph is a multigraph. Okay. But in the examples that I'm interested in, I don't allow such type of connections where between two nodes there can be more than one connection. So I'm interested in what are called simple graphs, where there are no multiple edges, and no loops. What do I mean by loop? We can very well have one connected to itself by something like a loop. So then the set of edges will contain one more element, 1, 1. So such a edge which is connected to itself is called a loop. So in my examples, I'm considering no loops and no multiple edges. So these graphs are called simple graphs. So what is the degree of a vertex? I mean, I'm not going to use it specifically. So the degree of a vertex is the number of edges connected to it. So for example, degree of 1 will be 4 here because there are 4 vertices which are connected. You can very well look at this set. So whenever 1 appears, we are going to count 1 towards the degree. So there are 4 appearances of a 1, 1, 2, 1, 3, 1, 4, and 1, 1. So the degree of 1 is 4. Similarly, the degree of 2 will be 4 because you have 4 connections. So 4, 2, 2, 3, 2, 3, and 1, 2. So a very basic theorem in graph theory would be the following. So 2 times the sum of degree of U, where U is a vertex, is equal to the number of edges, basically. Okay, so this is a very basic theorem, and you can take a look at it later on. So I'm not going to use this. I just wanted to mention because it's the first result in graph theory that one studies. All right, so what I'm interested in are called colorings. So I'm interested in coloring. So an N coloring of a graph G is a map, so C from V to the set N. Okay, this is a map from the set of vertices to a fixed set that we are considering here, which is the N element set 1, 2 up to N. A proper N coloring is an N coloring where no two nodes share the same color, where no two nodes sharing an edge gets assigned the same color. So in more mathematical term, if CU is not equal to, so here CU is not equal to CV, if UV, it belongs to the set of edges. So from where does the word coloring comes? It's very easy to assign colors actually. So for example, let's look at this graph. So this is a very simple graph. Then I can actually color the vertices. So if I make this green, then this vertex and this vertex, this vertex and this vertex, they are sharing an edge with the green marked vertices. So I cannot color them the same color as green. So I'm going to use a different color. I can make them blue. And then since the fourth vertex is not connected with the green vertex, so I can again color it green. So this is satisfying all the proper N coloring, so satisfying all the condition of a proper N coloring. And what we get here is a 2 coloring of this graph. So if my graph is G, then what I have is a 2 coloring. Okay, 2 proper coloring, and this coloring is proper. So I could very well have a non-proper coloring. I can have a non-proper coloring, so I can color it green. I can color this as well green, and then I can color this blue, and I can color this black. So this is a 3 coloring, but this 3 coloring is not proper because this vertex and this vertex, they share an edge, but they are the same color. Okay. So I need another concept called a planar graph. So this is very easy to understand. I mean, diagrammatically. So a planar graph is any graph which can be embedded in the plane with no crossing. Okay, no crossing among the edges. So for example, this is a planar graph because no edge is crossing itself. All right. This graph, it looks non-planar, but we can make this planar because, so let me draw this graph again. So I have this, and this. So I wanted to connect the vertex number 4 to the vertex number 2. So instead of connecting directly as a cross like this, I can connect this in this way. And I'm not crossing any of the edges. If I connect it in this manner, I'm not crossing any of the edges. And the graph that I get is the same as this graph. Because remember, the graph is defined by only V and E. And here the V is the same. And the E, if you calculate, if you list all the elements of E, you will get the same element. So I'm not changing the graph. So this is an example of a planar graph. I'm not sure if you are familiar with this example in school, but I mean, when we were young kids, we used to have this challenge. No? So if you have a graph, so if you have this graph, then the challenge was to draw this without lifting the pencil. And it was impossible to do this without lifting the pencil because we did not have the concept of this planarity. But this graph is nothing but the same thing as this. So you are going to connect it here. So this is equivalent as graphs. Okay. So as graphs, they are equivalent. Okay. So let's look at the results that we're interested in. So why were planar graphs and all this business of graph colorings introduced? Or I mean, why they are important is because of this result called the four-color theorem. So this was asked by Francis Guthrie in 52, and sorry, in 1852. So this is 1852, and this was answered by Kenneth Appel and Wolfgang Haken. I'm not sure when, but this is in probably in 1980s. I'm not very sure about this. So Kenneth Appel has a very nice book called Four Colors Suffice, which is about this whole business of four-color theorem. Okay, so what does the four-color theorem says? It says that every planar graph has a proper four coloring. So what is interesting about this result is that this was one of the first major theorems which was proven using extensive computer application. So what it boiled down was sort of like verifying several different graphs if they have a four coloring, and it was impossible to do it by hand. So Apple and Haken, they used a computer to do the verification. So this was one of the first results where a significant component of the proof involved computer verification or computers. Another very important result which used a computer was the Kepler's conjecture. So about sphere stacking in I think in 4 dimensions, if I'm not wrong. Anyway, all right. So we have these four color theorems. So as I mentioned here, no. So the first time this question was asked, it was a conjecture then. So the conjecture was that every planar graph has a proper four coloring, and it was a question asked by Francis Guthrie in 1852, and then it took about 130 years for it to be proven. So in the intervening 130 years, there were many attempts to prove this four-color theorem, and one of that attempt was by Gerrit Birkhoff as well in the 1920s. And Birkhoff, he introduced a function while trying to attempt to prove this. So the function that he introduced was called chi of z, which is now called a chromatic polynomial. So for a graph G, let chi G of n be this function, so which is the cardinality of this set. So C from V to N is a proper coloring, proper N coloring. And this number chi G of n is just the number of proper n colorings of the graph G. Okay, so this is called the chromatic number But we are going to identify this with a polynomial, and we are going to call this as the chromatic polynomial. So what we mean is we identify chi gn. Maybe I'll state the result that I'm interested in, and then I'll say this. So our first result, so this is a proposition. Our first result is the following. So if G is a graph, is a loopless graph, then chi of G of n agrees with a polynomial of degree V, with a polynomial of degree cardinality of V with integral coefficients. So if G has a loop, then chi of G of n is equal to 0. So what I was saying earlier was this. So this chi of G of n, we identify it with this polynomial. Okay, so the polynomial in the proposition. So we identify chi of G of n with this polynomial, and we call it the chromatic polynomial of G. So before going to the proof, okay, let me just rephrase this. No, so the four-color theorem, it stated that every planar graph G has a proper four coloring. So if I want to restate this in terms of this quantity chi of G of n, then what this says is that chi of G of n is greater than, chi of G of 4, is greater than 0 for every planar graph. So this is what the four-color theorem says. All right. So before going to the proof, I need to tell about two operations on a graph that one can do. So these operations are called deletion and contraction, and the operation is similar to the words that they sound. Okay. So by deletion, I mean we are going to delete an edge. So first is deletion. So for E and edge, the deletion of E is G minus E, G deleted E, and which is nothing but V E minus E. So how does this look like? So for example, if we have this graph, which has three edges, so three vertices U, V, and W, and if our edge is E here, suppose this is G, then G minus E will be this graph. So U, V, W will be here, but the E, the vertex, the edge E, we are going to delete it from the graph. So this is called deletion. The next thing that we need is contraction. So the contracted graph G contracted E is the graph.
Hello.
Yes.
सर एक्चुअली ये काइट फंक्शन थोड़ा समझ में नहीं आ रहा, थोड़ा ग्राफ में समझ सकते हैं?
Which function?
Chi function, chi g of 4 which is greater than 0.
Okay.
ये समझ में नहीं आया.
Okay. Yeah. So chi is just counting the number of proper colorings. Okay. So for example, if we have, let's look at a small graph. So let us look at this graph, and let's count the proper two colorings. Okay. So there can be only two different. So if I have, let's call this 1 and 2. So if I select two colors, say green and blue, then one particular coloring can be this, and another coloring can be the opposite one. So here this is blue and this is green. So this chi G of n, so here if this graph is G of 2 will be nothing but 2, because we have two colorings. So here the first vertex 1 will be green in one coloring, and in the second coloring the first vertex 1 will be blue. So this chi function is just counting the number of such colorings. So this is a very simple graph, but if the graph is more complicated, then it becomes much more complicated to color this. So what the four color theorem says is that every planar graph has a proper four coloring. So what it does not say is that how many proper four colorings there exist. It just says that there exists one proper four coloring, at least one proper four coloring. So chi g of 4 will be at least 1. That means chi g of 4 will be greater than 0 for every planar graph.
Sir, then chi g of n is always greater than 0, strictly greater than 0.
No, not necessarily. So I think I showed an example probably. Okay, I did not show. No, it is not necessary that for any value of n, it should have a proper n coloring. So for example, if let's look at an example. So here so here, for example, can this have a, so I mean, a very basic simple example would be a one coloring. So a one coloring cannot exist for this graph, it cannot exist for this graph, and it cannot exist for this graph as well. Because if you color anything by one color, say suppose one you are coloring with a green color, then two cannot be green. So a one coloring cannot exist for this. A proper one coloring cannot exist. But I mean, a one coloring can exist, but a proper one coloring cannot exist, because if you look back into the definition of a proper n coloring, what it said was that if two vertices, two nodes were connected by an edge, then the color of the two nodes cannot be equal. So for example, here this was a 3 coloring, but this was not a proper 3 coloring because these two nodes were connected by an edge. So they cannot share the same color, but this was a proper 2 coloring. So a very basic example for your case would be n equal to 1. So a one proper coloring cannot occur for many graphs. I mean, if it has one edge, at least one edge, then it cannot occur. Okay, coming back to the contraction operation. So G contracted by E is the graph obtained by identifying the two nodes incident to E and removing E. So if we look at the same example as before, this was U, V, W, and this was E. So what we are going to do is we are going to identify U and V. So the corresponding graph would be something like this. So we are going to contract this part. We are going to contract this part, and then U will be equivalent to V. So there was an edge between U and W, which is this edge, and there was an edge between V and W, which is this edge. But the edge between U and V, we are identifying that together. So this becomes this edge. The E becomes this. So this is called a contraction. Now I'm going to prove this result, this proposition, and which will be the only proof in this talk probably. So let's prove this. So the proof of the proposition. So if G has a loop, then this is trivial. So then chi G of n is nothing but 0, because for any loop, so if there is a loop, that means this particular vertex V, it's connected with itself. So you cannot color anything for this vertex. Okay. So this is trivial. So if G has a loop, then there exists no proper n coloring. So let's look at, so we are going to use induction on the number of edges. Okay. So for the number of edges being 0, then there are no coloring restrictions, right? So there are no coloring restrictions. So if there are no edges, then this is just a collection of nodes. The graph is just a collection of nodes, and you can color all the nodes with anything you want, because this is no longer connected with anything. So any coloring will be a proper coloring. So there are no restrictions, which gives us chi g of n will be nothing but n to the power the number of vertices. So each vertex you can color using n different colors. So all of these vertices you can color using n different colors. So the chi g of n will be n to the power the number of vertices. So what happens if there is one edge? Let's call this edge E equal to uv. Then what is chi g of n? So there is a graph, and then this graph has only one edge between u and v. So let's say d is equal to the number of vertices. Then this chi g of n will be equal to n to the power d minus 1 times n minus 1. So why is this? So all of these vertices, whatever is outside apart from u and v, you can color this using n colors. Each of these you can color using n colors, because it is no longer connected with anything. And one of these vertices, u and v, any one, you can pick, say you pick, you can color this as well using n colors. Okay, because this vertex u is not connected with any of the other vertices which have degree 0. So you have picked d minus 1 vertices. So d was the number of vertices. You have picked d minus 1 vertices and colored it using n colors. So the remaining vertex v, you cannot color using the color that you are using for this vertex u. So whatever is remaining will be the number of colors that you can assign. So the number of colors that you can assign to v is n minus 1. The only color that you cannot assign to v is the color that you are assigning to u. So chi g of n in this case will be n to the power d minus 1 times n minus 1. Okay, where this is a polynomial in n of degree d. Okay, so this is n to the power d minus n d minus 1. So this is a polynomial of in n of degree d, which is the number of vertices. So our induction step is done. The result that we wanted to prove was that chi g of n agrees with a polynomial of degree v with integral coefficients, and the coefficients are integers, and the degree is v. So for the induction step, let again E equal to uv, which is in E. Then we claim chi g of n is equal to chi g minus E of n minus chi g contracted E of n. So if we can prove this, then our result is proven, because this is a polynomial where, this graph g minus E is a graph which has one edge less than g. And similarly, this is a graph which has one edge less than g. So according to the induction hypothesis, both of these quantities will be polynomials of the number of vertices, which is the same as the number of vertices in g. Okay, and the difference between two polynomials will be a polynomial in our case. So if we prove this, then we are done. So let's see how we can prove this. So I'm going to just say this since time is also very short, and I want to show the reciprocity result. So let me just very quickly say this. So a coloring of G minus E, that means G deleting E, fails to be a coloring of G if CU is equal to CV. So if CU and CV share the same coloring, so this is UV and this is E. If they share the same coloring, then this coloring G minus E, which is G deleted E, fails to be a coloring of G, because in G, two vertices which are sharing an edge cannot have the same color. Okay, so we are overcounting basically, and the overcounting is happening where U and V have the same color, and this is exactly the proper colorings of G contracted E, because in G contracted E, we are going to identify U and V. So in G contracted E, we are identifying U and V. So that means whatever is the coloring of U will be the coloring of V. So in G contracted E, we are exactly counting these things, and this was overcounting this many. So to get a proper coloring of G, we just have to subtract the proper colorings of G contracted E. Okay, so this is the proof of the result. let's see how we can, what this gives us. So what we have is that chi g of n is a polynomial. Okay, then the next important question, the next natural question for a combinatorialist would be, do the evaluations -1 to the power mod of v, cardinality of v, chi g minus n have a combinatorial meaning? So if this has a combinatorial meaning, then we get a combinatorial reciprocity where we are going to connect a chromatic polynomial of a graph with some other object. So let me state the theorem, and then I'm going to explain everything that appears. So this is a theorem of Stanley from 1974. Okay. So let G be a finite graph on D nodes, and chi G of n, its chromatic polynomial, then -1 to the power d chi G of minus n equals the number of compatible pairs. So rho C, where C is an n coloring, and rho is an acyclic orientation. Acyclic orientation. So let me explain now the terms that appear. Okay. So any graph, you can give an orientation to that graph, right? So I mean, probably you already know what is a directed graph or what is an oriented graph. So this combinatorial reciprocity connects a graph which is non-oriented or non-directed to a graph which is oriented. Okay? It basically connects the coloring. So let's look at what an oriented graph means. So let us look at this example, a very simple example. Suppose this is our graph, and the vertices are v1, v2, v3, and v4. Then we can give an orientation on G. So an orientation on G through a subset rho of E. So for an edge E equal to vi vj, which is in E with I less than j, we direct vj to vi if E is in rho, and vi to vj if E is not in rho. So this seems like a bit more complicated, but what this says is that if we do this, so let's look at this this graph. So v1 and v2, they share an edge. So let us fix our row. So let's call row 1, 4, 2, 3, and 2, 4. So here 1 and 2, they are sharing an edge, but 1, 2 does not appear in row. So that means we are in this case. Okay, so that means v1 is going to v2. Next, if we check 1 and 4, they are sharing an edge, and 1 and 4 appears in row. So that means we are in the first case where E is in row. So that means our edge is going from v4. Sorry, our arrow is going from v4 to v1. And if we complete this, then we'll get something like this. Let's check for this. So 2, 3, it is appearing here. That means it is going from v3 to v2, the arrow. So G is oriented by directed edges from the smaller index to the larger index, and rho records the edges where this is reversed, basically. So always we are going from smaller to larger. So v1 is going to v2, v3 is going to v4, unless the edge appears in row. So if an edge appears in row, then we are going from the bigger to the smaller. So 1, 4 appears, so we are going from 4 to 1. 2, 3 appears, so we are going from 3 to 2. And 2, 4 appears, so we are going from 4 to 2. So this is what we call it orientation on G. Okay. So there is a connection between proper colorings and orientations which are acyclic. So what do I mean by cyclic orientation? By cyclic orientation, if I start from one particular vertex, say I'm starting from V3, and if I follow the arrows, if I continue to follow the arrows where it is going, and I reach back again on V3, then we say that the orientation is cyclic. That means I can go in a cycle and come back to V3. If this is not possible, then we say that the orientation is non-cyclic or acyclic. For example, here if I follow from V3, there is no way that I can come back to V3 because V3 will take me to V4 and I can either go to V2 or to V1. So if I go to V1, I again end up at V2. But from V2, I can no longer come back to V3 because the arrow is in the opposite direction. So if something like this happens, then we say that these orientations are acyclic orientation. Okay. So now if we come back to the theorem, what this is saying is that the -1 to the power d times chi g of -n, it equals the number of these compatible pairs rho and c, where c is some n coloring and rho is a acyclic orientation. So I have explained what is an n coloring, I have explained what is a acyclic orientation. Now let me explain what is a compatible pair. Okay. So an orientation and a coloring. So an orientation rho and an n coloring C of G are called compatible if for every oriented edge U to V in G, we have CU is greater than equal to CV. So C is a coloring that we are assigning on the graph G, a proper n coloring. The pair rho C is then called a compatible pair. Okay. So let's go back to the theorem again. So what we want in our reciprocity is we want a graph which has orientations. So for example, a graph like this, and the orientations are given by this row, where our row is taken to be this in this example. And then on this graph, say let's call this graph G. On this graph G, we are giving an n coloring, and we are calling this n coloring to be compatible if this happens. So if U and V is oriented in the graph, so if there is a edge which is going from U to V, then the coloring that you are assigning on U has to be greater than equal to the coloring that you are assigning on V. So remember, the coloring was, I mean, I am using the colors, but the coloring was essentially a function from the set of vertices to the n set. So this was the definition of a coloring. So this was the definition of a coloring. So basically, to each vertex, I'm assigning a number from 1 to n. And if the number that I'm assigning on a vertex U, if it is greater than the vertex V, then for the orientation to be compatible, we need the arrow going from U to V. That means the arrow has to go from the bigger color to the smaller color. So such a compatible pair, such a pair, rho and C, is called a compatible pair. And the reciprocity theorem is basically saying that to count the number of compatible pairs, you just have to know what is the chromatic polynomial. And if you know the chromatic polynomial, then if you take the chromatic polynomial in negative integers and normalize it, you are basically getting the number of compatible pairs. So I'm out of time. This is a non-trivial example, which I want to stop at this example. There are other interesting examples involving posets, where instead of chromatic polynomials, we get something called order polynomials. And if you know what is a polytope, then there are interesting reciprocity theorems in polytopes, where instead of chromatic polynomials, we are going to work with something called Ehrhart polynomials. And all of these polynomials, there are connections between them. So if you are interested in such type of things, then I strongly recommend you take a look at this book by Beck and Sanyal. It's a very nice book. And all of these connections between chromatic polynomials, order polynomials, Ehrhart polynomials are explained very well in this book. So I'll stop here, and thank you so much.
Thank you, sir.
Any questions?
It was nice.
Oh,
And I think I have met Manjil Saikia while in when he was a student in Tezpur University. I visited Tezpur University once.
Yes, sir. We met when you came for some workshop. You were teaching in a workshop.
Yeah. I gave an interview which was published in Ganit Soro.
Yes, sir. Yes.
I'm glad to see the great progress and wish you further progress.
Thank you, sir.
okay. So if there is no questions, so let's thank speaker. You just unmute your mic and clap for the speaker for this nice talk.
Yes, sir.
Thank you.
So thank you, Manjil, for delivering this nice talk.
Thank you so much.